I will first give a presentation and then I will have a short view at the data set. So I think we can start with the presentation. And the topic, first of all, I want to go into the research topic. And here we derived a new method, which is based on fluid theory to determine adsorption isotherms. There are probably two ways you can do it. The standard way is doing an atomistic simulation in Monte Carlo simulations. And our new method that we want to propose is using classical density functional theory. So chemists usually refer to density functional theory on an electronic level. Here we really go into an atomistic level. So we look at atoms or molecules. And we want to make a proof of principle that we can use this method to determine adsorption isotherms in, for example, covalent organic frameworks or metal organic frameworks, zeolites, whatever you want at the end. Okay, so what are we doing? We use those two methods. Like I said, the standard way, which is Monte Carlo simulation. And the new possibility would be classical density functional theory. And why do we need a new method? If we can use this method, it's really computationally fast. So if you calculate it by Monte Carlo simulations to get a full adsorption isotherm, you need like 1 week of calculation time, depending on the structure and everything. But with classical density functional theory, you can do it within minutes or half a day. So it's really a large difference in time. And if you look at those new functionalized or those new materials like a COF, and a covalent organic framework is close to a metal organic framework, then you have the same feature that they are built of those building blocks. And by having a lot of building blocks, you have a large variety of those porous media, which means that you can use fast methods for maybe screening, and you can also get information about the properties of the fluid. So there, you can see it as a door opener to new methods. So that's the reason why we are doing it. Okay, so let's look at those two methods. In Monte Carlo simulation, we have an atomistic potential. And then by drawing random numbers, we insert molecules in those simulation cells. And then we have to calculate the potential to every framework atom. And if we have more than one adsorbate molecule or atom, then we have to also calculate the fluid-fluid interactions. And then we have to generate a lot of microstates and do the averaging. So that's quite a large amount of calculations that you have to do. And therefore, it takes a lot of time. And you have to also think of sampling this statistically. So you really have to make sure that you sample long enough, which you probably not know by starting it. Okay, let's look at the new method. As I said, it's from classical density functional theory, which you can use at almost all problems where you have an interface. So droplet coalescence or adsorption isotherms, or if you look at micelles also, then you can use this. We have to describe an inhomogeneous system, and it's an open system, and therefore we can use the grand potential. And this here, the squared brackets, they indicate that we are using a functional, and the grand potential is a functional of the density. And the density, we can now use the density profile to get the free Helmholtz energy. And this is from an equation of state, and we use a PC-Saft equation of state. And then we have those bulk properties here and the external potential. By reorganizing this, we can get the Euler-Lagrange equation. And this means that the current potential is in equilibrium, it's minimal. So we can then divide our simulation cell in those volume cells. It's quite more than those. So like I'm not so sure, 5,000 or whatever, so larger number. And now we just look at a small amount here. At the start of the simulation, for each voxel, we have to calculate the potential. So we have just to do it once because the point is fixed, and then we can store it in the memory. And then we just have to iterate and to minimize the density profile, and we get our density profile, and we can integrate over it, and then we directly get the absorption isotherm. So then you also see it will converge to a certain amount, and then the calculation is finished. So you don't have to sample it somehow. Okay, by doing this, you can use it for mixtures, or you can use it for pure components. I just put here the pure components, and we see an absorption isotherm. So here we have pressure, and here we have a certain unit of loading, which is molecules here per kilogram framework. And for this covalent organic framework, we can see that the lines are density functional theory calculations, and the points are Monte Carlo simulations. So we can see that even for a charged molecule like nitrogen, we have a quite well agreement between those methods, and it's really fast. And you also have to keep in mind that both methods, they are purely predictive, so there are no parameters that are fitted to match anything. Okay, it's just the fluid parameters that you have to fit once, but that's already done in PCSAFT to equilibrium properties. Okay, let's see the data, what we did. We have those points. Here I put a link to the data set or a QR code, and you can find it really easy. You can have a DOI here, and you can also Google it, and yeah, you can find it on the first page, I think. And we think we can make it reusable by adding those Jupyter notebooks. And the data set is hosted on Daros, which is, let's say a child of Dataverse, which is developed in Harvard, I think. And we put a lot of files on there. So if you do molecular simulations, you have a lot of input files. And to reproduce it, normally you have to type those values, and it's really annoying and also quite easy to make mistakes. So we put all our input files, you can directly download them and put them in your molecular simulation code, which is also online, and you can get it. And by using the same version, you will probably really reproduce those results. We can also put on a lot of metadata and all the software and methods that we use. Okay, so I think as we are online here, I can now go into the data set. Here, first of all, I put the publication, and also here we link in the supplementary information, like you're quite used to it. On the bottom here we have all those values, like it's the usual way we put them, and you can retype them, but you see it's quite a lot of numbers, and not the easiest numbers to type probably, and then you can just download them and retype it. So that would be the old way. We also do this because people are used to it. And here we have some additional graphs. I was just screening them, and then you see you get a DOI to the data set. So here, this is Daros, which is hosted at University of Stuttgart. And you have an additional homepage, and all the data is there. And I think also for parsing it and so on, Daros is quite in a standard format. So you can easily access it, and there are also APIs to get data from there. So now you can here see a short description, and there are also some keywords if you use, if you want to find it. And then you can also look at other metadata. Like I said, here information about the authors. You can also see again keywords, and they are also linked, so you can get an explanation for them. You directly have a link to the publication, and here, for example, you see all the software that we used with the version numbers, so you really know what you do. Because sometimes molecular simulation codes, if you change the software, then you can have different results. So you have to be really careful there. Okay, so we can now shortly look at the files, I think. As I said, we have this Jupyter notebook, which will show all our results, and you can also download it and edit it. And then we have structure informations that you can download. And you have also the files for the molecular simulation codes. So by downloading all those files and putting them in the code, you would be ready to go. And as I said, this is like a force feed file, and you have to bring it in the format that is given by the code. And yeah, it's also easy to make mistakes there, and if you want to reproduce data, it's quite annoying to get it in the format and so on. So putting the things there, if you start a molecular simulation study, you often have to reproduce data, and that will be a really fast track to get used to it, I think. Okay, then the last thing I want to show is the Jupyter notebook. Here it's just a PDF file. But normally in Jupyter notebooks, I think a lot of people are used to them. You can use code and also text description. And we wrote the notebook in a way that you can use it without installing all the packages. And you can also activate them if you really want to do the calculations. And then we have some short description. And one critic from the talk I was giving in Hanover was that it's probably not so easy to understand the data set without reading the publication. That's really a thing. But by using the publication, I think you will be quite able to reproduce or to understand what we did. So if you now want to start and maybe reproduce something, you can really download the code. Here you have all the input values linked with the notebook, and you can also reproduce or add your own data to a plot easily by reading in your data and applying it to the notebook. We also use the method for mixtures to determine mixture isotherms from scrolling. From pure component isotherms, which is a calculation style, which is called ideal adsorbed solution theory. And you can also reproduce those calculations directly in the notebook. So if you want to do a similar thing, then I think it's really easy to get your data and to get your input. And I think you can also start from this point. And I think that will be really valuable. So I just remember my time as a PhD student at the start. You always have to get your first steps ready. And I think maybe, like I said, it's like said before, it's some kind of effort that you have to put in. But looking at FAIR data, maybe you don't get back the effort on yourself, but the future generations, they will really appreciate what you did, I think, because it will save you a lot of time getting started, probably, especially in molecular simulation. And yeah, I think this will be quite valuable. So the work I presented is part of Sonderforschungsbereich 1333 at University of Stuttgart, which is funded by DFG. And it's also, like I said before, quite a pressure to produce FAIR data. But looking back, I really appreciate doing it. And I think for the future, it will be useful for people. And then the data will become a lot of more accessible. And I also think one critic might be that we did not link the code for the density functional theory calculations, but I just re-thought and we already published it now together with PC's after equation of state. And probably it would be good to make a new version of the data set. So the data set is also in a versionalized style, and to add those code lines or to link the code. So you can also reproduce the density functional theory calculations. Okay, so I want to thank again everyone for joining.